and you can have the pump storage projects. These are the category of projects, but every such project requires dams to be built, storage to be built, canals to be built, depending on the sector it is benefiting, irrigation, power, navigation, or whatever it is. The new category of things which have come up in the last 2 or 3 decades are the lift irrigation schemes, where you have huge pump houses and we are trying to lift water to upland areas. Why are we requiring this? Because basically the command area is higher than the normal reservoir levels. So now how to take the water to the uplands where we can feed the area. So we are going more and more for lift irrigation projects. Of course, it is having more of a hydromechanical component, which has a very big contribution to that. But then this is coming up in a big way in the states of Maharashtra, Andhra, Telangana, and many other states. And it is catching up in a big way. Now, coming to the water project cycle, basically from concept to commissioning is what is given here. I can convert the water to watts, or I can convert the water to drinking water, or for irrigation, or for industrial supply. The cycle remains the same. The components will change. Basically, if I want to see what is into a hydropower generation, it is basically I take the water to the headworks, through the headworks to water conductor system, and then it goes to a powerhouse, transmission system, and it provides the needed electricity to the consumers. And same thing, if I want to see how it goes to the homes and farms and industries, either I can take it by gravity, by canals, by pipes, or by lifting. So end product is drinking water supply, irrigation, or industry. So broadly, these are the contours of the entire development of the water resources. Now coming to the components of it, what are the infrastructure development that you need to do? If it's a surface project, the entire list is given here. What all structures you are required to do. So you need dams, barrages, or any other appurtenant structure. Then you need sediment management measures. You need a conveyance system. It could be a piped water distribution network, or it could be a canal, pump houses, embankments, drain. I think all these are well known to you. If I go below the surface of, I need additional components in the form of tunnels and caverns and vertical shafts, inclined shafts, and all other extra provisions for accommodating the various components of the system. Now, with this, give a small background about the entire infrastructure development in the water resources structure. What I do is I go component by component, touch upon few slides, and move forward. Now coming to dams and barrages and appurtenant structures. Now coming to the development of this entire dam engineering, you can see that significant advances were made somewhere in the 19th century, and then people started thinking of more of 1 and 2 dimensions. They started thinking on 3-dimensional approach of thing, and then we started about the seismic analysis. Seismic analysis was pseudostatic, and then subsequently Koina happened, and Koina changed the way we looked towards the seismic aspects. So now we have high-speed digital computing systems through which you can do a lot of modeling and try to see that we are giving a best robust design for any structure, which can stand for perpetuity. Now, it's a paradigm shift in the dam design. What is it? Earlier, we used to say that a dam is designed for 75 years or 100 years or so. No, that is the design life approach is now being replaced by life cycle approach. That is life cycle management based. If I operate and maintain the dam to the best possible manner, I can keep that asset for perpetuity. And Kalani Dam is one such example. Though it's a small dam, but then that really teaches us that we can really maintain dam for lifetime if we are trying to have good management practices. Now, as I was mentioning, in the dam design engineering, a lot of advancements have taken place. We have many tools coming up. Earlier in the 80s and 90s, when we used to design a dam, we used to do everything manually and then came the spreadsheet, and then now we have many tools which have come up for static and dynamic analysis. And now dynamic analysis has become mandatory as far as the standards are concerned. So you can see how the numerical tools have been put to use for design of the dams. And I'm very happy to see that all these are being done by our CWC engineers for the last 2 decades or so. And many of these dams have been, and many of the other PSUs and state governments have benefited from these advancements. Now, one particular example is something called creep. There are many problems in a dam design and foundation. I mean, you have a lot of river-borne material, you try to excavate it and try to fill it up. And then you have the abutments and slope instabilities. So one of these things is a creep which happened in one of the project. The right bank was creeping and trying to move. And that was one of its first of its kind issue which came up. And the modeling was done by CWC experts, and then finally solutions were given for that. So this is just to have a glimpse of what are complications you have or challenges you have when you go. Today we have CWCs handling Lakwar project or Renuka project. Even Lakwar has its own set of challenges. I mean, we had not many challenges in the past also in many of the dams, and same thing continues with every other dam. No two dams are alike, no two powerhouses are alike, or no two projects are alike. So that's the thing. So the ingenuity of the engineers in Central Water Commission is well appreciated outside because of all these advancements and state-of-art solutions that we provide to them. Now with the Koyna Dam changed the entire ecosystem of the seismic studies. We had standing committees, and today we have the National Committee on Seismic Design Parameters headed by member DNR Central Water Commission, and we also have come up with guidelines for that. So with these guidelines, we are now able to really find out what are the seismic coefficients for the design of dam and other structures. So alpha H and alpha B we are able to find out and then give. Now under the DRIP program, we are going one step forward, that we are trying to see how we can develop a seismic hazard analysis information system. So we can find the seismic coefficients anywhere for any structure in the country. So IIT Roorkee and CWPRS Pune, they are onto it. And that also is going in a very advanced stage of development. So we have come a long way as far as the seismic studies are concerned. Now, with that, I move on to the stability of slopes. Stability of slopes has been a big bone of contention in many of the projects. Whether you take, we had something in Dholi Ganga when 90s when we were on Natpa Jakri, we had a major slide upstream of Natpa Dam. Then you know the famous Pune Sanchu case. Pune Sanchu 1 was stalled for almost 6 to 7 years because of a landslide. So this has been a very common issue in many of the projects. This is a typical case of the Pune Sanchu Dam project, where we had a series of slides. 2013 we had one, subsequently we had one in 2016 as well. And not many investigations were done. And the state-of-art radar instrumentation has also been deployed over there. And because of this landslide, the entire diplomacy between India and Bhutan also came to a sort of a bitterness, because of which they started to shift to a barrage downstream of this. And then CWC had to really contest with them that the barrage is not an ideal project, as an ideal structure. It has to be a dam. And finally, after 5 years of communication and convincing, the whole thing has come back to the original dam site, and works are going to start, or it has started, I suppose. But then, how a landslide or rock slope can really change the entire planning. So when I said the water cycle planning to commissioning, planning is the most important thing. Any fault in the planning will really take it forward to the entire stage of the project, and it may get stuck up somewhere during construction or during design. Now question is different, whether this site was ideal or not. I am not going into all these aspects, but point is, when we are really doing a recce or an investigation at the initial stage, we have to see about the stability of the abutments upstream at the dam site, upstream and downstream of the dam site. In Natpa Dam, we could sort it out very nicely, because our own engineers, we all did together everything. Natpa Dam slide was sorted out. But somehow here, being an international project, there are not many issues into this. Now, coming to slope stabilization, we have lot many techniques. We can do it through micropiling, we can do it by cable anchor installations and all. So there are lot many techniques there that goes into stabilization of the rock mass. Now, basically, there is a difference between rock and rock mass. When I say rock is an individual piece of rock. It can be a granite or gneiss or anything. But when I say a rock mass, it's a grouping of all the mass, all the rocks which are forming part of that setup, geological setup. So the rock mass stabilization can be through various ways, which I have showed here. What happens is basically it's the geology. Geology has to be the most, geological investigation is very, very important. What are the various joints, weakness zones and other things, and what is the dip and strike of that. And whenever you install these cable anchors also, you need to see that you are not going along the joints, but you are going perpendicular to the planes which are cutting the slopes. That's enough for slope stability. I come to the powerhouse structures. Yeah, this is an entire section of a Francis unit or a Pelton unit. You may be knowing that we have different turbines, Pelton or Francis. Each has its own way of functioning. This is one of the most typical structures which you have to really design. As a civil engineer, our CWC engineers have a major role to play, because starting from the top exciter, then you come to the rotor, then you have the stator foundation, and then you have this spiral case foundations, and then draft tube. So you have huge load transfers happening, which I have listed on the right side of the slide. So the project is constructed from the bottom to the top. So we start from the foundation, whether it is surface or underground powerhouse. We start from the bottom, start building one by one, draft tube, then we come to the spiral case and the other structures above it. Now here is most important thing is we need to have very good coordination or synergy between the civil and electrical people and hydromechanical people as well. So that's where it's challenging that all the three teams together work together and then see and try to see that no single item is missed in the entire installations. If you miss some pipe in the system, there are numerous pipes and items, components which are there, which needs to be accommodated to these mass concrete and all. So one has to be very, very careful. So CWC, CA has a very good coordination in this, and we try to see that things go as per the drawings. We also have the manufacturers, that is, it can be BHA turbine, or it can be as from any turbine. So the third party which is there is the turbine manufacturer, who has to also be part to this design. Now, what's most important is you build the civil structure, but then installation of the turbine, the alignment has to be perfect. If there is slight mismatch in the alignment, you are going to have vibration, or you are going to have some issues. There have been projects in the case in the country, abroad as well. So in the country, we have only one case. Yeah. But abroad, in Russia, you had a major failure. If you remember, in 2009, one of the powerhouses collapsed. Entire 70 people were killed because there was certain vibration going on in the turbine. There was fatigue. Because of fatigue, there is something called there is a turbine cover on the top of it. The turbine cover blasted, and that entire water which was there in the water conductor system, it came up and it spread into along with the rotor. Rotor was around 900 tons. The entire rotor was blown into the machine hall, and around 70 people there were killed. Entire powerhouse was flooded. So the degree of fineness in your alignment of the shaft and other components is very, very challenging, and that's where you have to be very careful. We also had, during my tenure in 90s, we had vibration of one of the projects in Andhra Pradesh, and that project vibration of the turbine was not being able to, they were not able to fix it. Then they approached Central Water Commission, and then we saw that there was certain problems in the penstock. Again, the frequency is important. Now, the frequency of all the system should be such that there is no resonance happening in the system. If the penstock frequency, the turbine frequency, the other structures' overall frequency should not match. So frequency analysis in the powers also is very important. And there we could see that there was certain frequency matching, and that's the result. We had resonance, and because of resonance, the anchor blocks were cracking. And then finally, we had to see that we tried to change the frequency of the penstock anchor block system, and as a result, the vibration was controlled. So we have numerous such problems in the power structure. Now comes another case of flooding of a powerhouse in Himachal Pradesh. That is Dehar Power Pump. Dehar Pump project in Himachal Pradesh, where we had flooding, and I was asked to go along with the CA engineer to go and inquire about it. And then at that time, what we found was, normally what is happening, I'll tell you. We all are civil engineers here and mechanical engineers here. So normally there is a tendency of putting a blame on the civil structures, and you need to be very careful that civil engineers have to be very careful in defending a power project, because many things are civil structures, and if you are not building it properly or not doing it properly, that could be something. Now, what used to happen was, we used to have draft tube gates, only one draft tube gate for a powerhouse, and that used to be operated for all. Even now, I don't think we never had any draft tube gates for all the gates. The water level in Satluj raised significantly, that by the time they could close the draft tube gate, the water had entered to the system. The point is, even if it enters the system, it cannot enter into the powerhouse. Why did it flood the powerhouse? I said, sorry, I don't agree to your contention that the draft tube gates are the victim to this. Then we went into the powerhouse, and I was going to the powerhouse. I know the turbine cover is some very sensitive part of it. I asked them to just show the turbine cover. We saw the turbine cover, the bolts were sheared. The bolts were sheared and the turbine cover got lifted up. So it is basically the turbine cover which bolts got sheared and got lifted up, and water moved into that. Because of very high head in the downstream of the Satluj river, the entire pressure has come into this powerhouse and flooded. And finally, with all reasons and technical background, I could convince them, and the report came out that the turbine cover which is the culprit and not the draft tube gates. So we need to be very deep into the things that we are able to see, that we are trying to see what is the real cause of such failures or challenges. So the powerhouse itself has not many things. I'll stop it here. But kudos to our CWC engineers. We have been able to do numerical modeling of the generator panel foundation as well. And coming to the underground powerhouses, I think we started venturing into underground powerhouses somewhere in the 80s. Chuka in Bhutan was one of the first underground powerhouses where the Central Water Commission had really ventured into it. And we built that project successfully. Somewhere in the late 80s, we inaugurated, both the countries inaugurated that project. Subsequently, in 90s, we picked up. 90s, we had Sardar Sarovar, we had Nandas, we had Sri Salam, and we had Paikara, we had many projects which had underground powerhouses. See, every time technology evolves in Central Water Commission. Overnight, you and I cannot become an expert in groundwater and underground technology. So we started Napa Jakari. I would appreciate SJVN, they have very good fleet of engineers, and Napa Jakari had very complex underground structures with them, with a very long headway of 27 kilometers. First time we were building that. The caverns was 25-meter wide cavern. But how it started was, we had first Sadasivan project which had one cavity, and we could do that. We had some challenges in the upstream phase of the Sadasivan project where we had cracks. We used to call them A, B and C cracks, and how the cracks of the walls were treated and all, that was a big example. Papers are available on that. Then we came to two cavities. That was Napa Jakari project where we had a powerhouse cavern and a transformer cavern. But then we didn't keep it parallel, we kept it something like this. So that there is no, if you build two cavities and the intermediate rock pillar collapses, then there is a huge disaster again. So we built something like this, powerhouse cavern. We had a transformer cavern, which was slightly above on in the Napa Jakari case. So then we ventured into three cavities. That was in Sri Salam project, where we made powerhouse, transformer, and a surge cable. So here you can see center is the powerhouse cable, right side the surge cable, and the left side we have the transformer cable. But that they were all almost parallel. So that had its own share of challenges. Now, just for people who want to know what is inside the power machine or cavern and all, we have the entire structure. What is built on the surface is built underneath. We have the entire starting from the foundation till the top of the powerhouse. We have building into this. Again, for modeling this, we have for the entire cavities, we have various packages for modeling the cavities in the rock. That is, we have the UDEC, 3DEC, and all many other softwares from rock science also have come into picture. And each of these components for stabilizing the cavity, we have rock boards, cable anchors, steel fiber reinforced shotcrete, lattice girder, rib reinforced shot. Many of these things have been designed. For your kind information, steel fiber reinforced shotcrete was we introduced first time in Sri Salam project in 1994. We were not manufacturing steel fibers at all in the country, so we had to import around 100 tons of steel fiber from Belgium, and we tried. Earlier we were only doing weld mesh shotcrete, where we had weld mesh and we were shotcreting on that. But then steel fiber gained momentum during 1990s. So 94, when they saw that CWC has really gone for steel fiber reinforced shotcrete in Sri Salam project, everybody, NHPC, everybody started going for steel fiber, and steel fiber industry became a big industry in the country. So today, anywhere we are only giving SFRS. We don't give the normal until unless it is required because of the situation what we are dealing. Now, even then, those days, there was also a concept that we were building the entire structure. You saw this, the entire structure coming up, and then only the crane we are getting the crane for our erection of the turbines and other things. But then we also attempted that why not we go in for a rock ledge where we can keep the cranes in the start itself and then try to use the crane right from excavation itself. But then it could succeed in one or two projects, but then people in Himalayan regions were very skeptical about the geological conditions, and so the rock ledge is not being commonly followed nowadays for keeping the crane beam right in the start of the excavation. But this is followed in many countries around the world. This is the extent of modeling that is required, which some of you may be doing it, performing this, I am sure. And then wherein we go in for the stress analysis, because if you try to dig a cavity, you have some stresses developed around it. You need to find out the factor of safety envelopes and try to see that they are all being properly addressed. And this is the situation where we first had the entire between two caverns in Sri Salam project. We had the right one is the surge cavern, left one is the transformer cavern. Now this pillar was very short. Now always there is a what we call sort of a debate between the electrical engineers and the civil engineers. I mean, we want the caverns to be as far as possible, but then because of the bus duct cost, what happens is the electrical engineers want the powerhouse and the transformer cavern to be as close as possible. But then there is always an optimization that goes into it. But nevertheless, when we have a very high surge cavern, the pillar is normally very, very sensitive to distressing. And we had a huge distress when we did the 3DEC model in this. We had the huge distressing of this pillar because the height of the surge cavern was 75 meters and this pillar was hardly, I think, 40 meters or so. And that distress, based on the numerical modeling, we could see that we have to really strengthen the entire pillar. And that's where, besides the rock boards, we also get cable anchors, which was end to end, and we tied it towards the transformer cavern side. Today, this project is standing. I mean, the pillar is intact for the last 20 years. It was commissioned in 2002 or so. So we have to create solutions based on the problems that we are anticipating. And this is a network of activities. Now, but now we have moved further with this comprehensive analysis of all the tunnels and caverns, which our people in Central Water Commission have done for the Bhutan project. This is the extent of tunnels and caverns which we see in any underground powerhouse. And you can see, I mean, what would be the cover, vertical, lateral covers and all those things. It's really a very comprehensive desk study which one engineer has to do, and our people have been doing this. Now, what happened was during this project, I think you may be aware, some of you may be aware about this downstream surge gallery which really collapsed in Punasachu, and then we had this huge fall. Subsequently, a huge wall was created, and that is contained. And now this, once you have this such a phenomena, you are losing a lot of area of the surge tank, and for that they had created some extra additional surge gas chambers have been created in this system to compensate for the loss of that plant area. So finally, the whole thing has been sorted out. And here what happens is basically lot of mind, it's all mind game and technology and innovations that have come into play. And that's where the team has been successful in doing this, and finally it has been commissioned now. That's the end of powerhouse now. We move to reservoir sedimentation, which is a very, very serious topic now. As you all know, sedimentation can create lot of loss of storages. It can create problems to your electromechanical and hydromechanical components. And you can understand the seriousness of this reservoir sedimentation by looking towards the Iyer bulletins which have come out. You can see in the last century we only had around two Iyer bulletins dealing with reservoir sedimentation. But now if you see in this first quarter of this century, we have around 4 bulletins, Iyer bulletins, which have come out on reservoir sedimentation and how to manage the sediments in reservoir. In Central Water Commission and the Ministry, in the last 10 years, we have come out with 3 of these documents. I think you all will be knowing. CWC came out with this 19 publication. Ministry came out with this 2022 publication, and we have this reservoir sedimentation compendium, which is a regular feature, which came up in August 2024. Quite a lot of information has been generated out of all this, but still we have a lot of problems. If you can really see a storage scheme, a storage reservoir, if you see what you are having the designed sedimentation rate and what is the actual sedimentation rate is far, far more than what has been observed. What would be the reason now? I throw this question to you. You have 5 times more than the design rate of sedimentation. So what would be the reasons for this? Just to wake up some of you people who would like to go into slumber, so I thought let me ask you a question now. What would be the reasons now?
Deforestation?
Yes?
Deforestation.
Deforestation, okay.
Land use change. Land use land cover change.
Land use land cover change, okay. So when we were designing the project, you say the land use land cover was different than what it happened during the implementation of the project subsequently. Fine. Number 2 is deforestation is another phenomena. What else? Maybe your observations also were not observations which were there. I mean, we have really not factored it properly. Maybe possible.
Proper silt flushing arrangements.
No, I'm not going to. We are going to run another river scheme. No, I'm not going to run another river scheme. I'm talking about storage reservoir. I have a dead storage. I have a live storage, and so I'm talking of the storage scheme. I'll come to run another river later.
In measurements, 2 aspects are there. One
Yes.
is for the suspended load, there is always lot of issues in the measurements as well in sampling. Another area is the bed load. Bed load measurements is never done and it is estimated. So there is always a gap in estimation and what actually we are observing in the result.
Exactly. So basically, that's also one of the factors because bed load we take 10%, 15%, 20% as a percentage of the sediment. So as a result, we don't know. But then what happens is bed load is basically huge boulders come in. The river also has three regions I would classify: upland, midland, lowland. If I see Himalayas in Uttarakhand, Ganga in Uttarakhand, Ganga in Lucknow, Varanasi, and Ganga in Farakka, they are all different as far as the sediments are concerned. So I don't see the bed loads are very high in the upper reaches. But then what we do is we calculate as a 15% of the sediment. So okay, said bed load is really a approximate figure. That's one thing. But what fills up the dead storage is apart from the bed load, we have lot of other suspended and in between sediments between sealed to pebbles, sand, clay. So we have not many things. So estimation of these quantity is also paramount, that we do it more accurately, number one. Of course, the most important thing is the anthropogenic cases, which was mentioned about the development subsequent to that. If I go to any project in the Himalayas, we see lot of roads being built, lot of other things being constructed, the entire thing is coming down and going. But then we don't have storage projects. We only have Tehri or we have Bakaranangal or something which are storage projects. But most of them are run-of-the-river schemes. But then there are factors, and these other factors, our sedimentation issues are even had ICOD has appreciated that India has developed significant information on sediments. So they have appreciated in one of their ICOD bulletin about our approach to the sediments. But then we have a long way to go. We have to find what are the reasons that we are really having these issues. Fine. Coming to the National Framework of Sediment Management, Ministry released in 2022, we have various approaches. We can reduce the sediment yield from the watershed, well-known fact. Then we have to minimize the sediment deposition, fine. And for that we have various approaches. We bypass the sediment and all those things. Then we have, as mentioned already, flushing or sluicing and other things. And then other aspects are mentioned here. I'm not going to each one of them. But then there's a distinct difference between a storage scheme and a run-of-the-river scheme. I'll now come to the run-of-the-river scheme. What is the run-of-the-river schemes normally we have is that it has a diagonal storage, doesn't have a storage at all. So sediment handling in a run-of-the-river scheme is more difficult or more important compared to a storage schemes. If we don't do, this is the outcome that you are saying. You have all the turbines eroded. You have the sediment chamber. You can see what is the extent of silt deposition which has taken place in the sediment chamber. So this is something pictorial which I tried to put it across today. I mean, months back, 2-3 months back, I tried to develop this along with one of our CWC friend only. But then this explains everything. What happens in the catchment? We have the bed load, we have the suspended particle, everything coming from the catchment coming to a dam. Now, dam is not a place that we need to store the sediments as far as the run-of-the-river scheme is concerned, because we don't have a dead storage at all in the run-of-the-river scheme. It has to, anything which comes in has to go out. So, what all techniques we are adopting in this project should see that the bed load is there, should be flushed down, the suspended sediment should be flushed down. Now I have this water conductor system which goes into the powerhouse and then discharges back. What happens is, in spite of the best possible management in the reservoir by the dam sluices, whether it's bottom sluice or whatever way, we see that a significant amount of undesirable sediments enter into the power intake and goes into the water conductor system, and that's what creates a lot of problem. And that's where we have to have something called settling basin, and the settling basin is one which tries to settle all the suspended sediments. Now, settling basin also is a very costly component. And if you have to really design a settling basin, what we do in CWC? What we do in CWC normally for a settling basin? It's such a complicated structure, cost expensive, but then what we do in CWC, what have we been doing so far? Bataiye, can you tell me?
So either we provide the desilting chamber to remove the silt, or we improve the quality of the turbines and vanes by increasing the grade of steel.
Fine.
These are the two options which are available.
Fine, absolutely. See, that's fine. That what you said is absolutely absolute fact. See, either I improve the turbine thing so that it can absorb any damage which is possible, but that metallurgy is far behind civil engineering. For your information, metallurgy is far slower than civil engineering. Metallurgy people have nothing that can really remove the hardness of a quartz particle. Quartz particle hardness is 7 on the Mohs scale, and if there is no material which really, it's only the coatings which are there available. If you go for a normal nickel chromium turbine, it doesn't have that hardness of 7 and all. So what they do, they put a coating on top of it of any of this tungsten carbide coating and all those things and try to improve. But even then, it is not able to withstand, and lot of pitting and all happens. And recently, 1 month back, I was asked for some case where a lot of pitting has happened, and I was to consider for that. But then, point is, that's metallurgists don't believe on metallurgy. They won't be able to compete with your requirements. What best we can do as a civil engineer has to come to the fore here. Best possible sediment management, flushing, sluicing, other thing we do at the dam body. But even people have tried by bypass channels in various countries, but the suspended sediment is what really we are able to contain that. So when it goes into this, settling basin is must. Again I'll come to one more characteristics of the river. River, as we all would have observed in the site, would have coarse, medium, fine. Got it? If a river has 90 to 95% fine, what is your judgment of the river? Can anybody tell? A river, we are measuring discharge sediment observations in all the HO sites in our country as a CWC site. If my river has a fine sediment of 90 to 95 to 100%, what is the inference drawn from that?
In that case, the desilting basin will not work.
Desilting basin is not required at all. Even if you provide 10 kilometers of desilting basin, the fines will not be settling there. It will just go into the turbine. Got it? So that is one case where I don't need a desilting basin and spend 200 to 300 crores if my river is only having 90 to 95% of fine sediment. Now I change the whole equation. I have 90% coarse, only 10% fine. Then people say that I can take reservoir as my settling basin. They cannot take reservoir as a settling basin if there is 90% coarse, because coarse will certainly enter into my settling basin. And what is the threshold of sediment that can enter the turbine? We don't allow in beyond a particular ppm.
0.02 say Java.
In ppm, I'm asking in parts per million.
3,000 to 4,000.
So whatever figures we are saying, I mean, if you really work out, you cannot really dispense the settling basin until unless your sediment characteristics are favorable to you. Okay. So whenever any project comes to you saying that I am removing settling basin or I am keeping settling basin, you need to see the characteristics of the river sediments. Now, my thesis has been on this because I have done my doctorate on this only after retirement. So what actually happens is, today you have something. Today you have certain river characteristics when you are designing. Today, suppose for example, Pune Sanchu, you designed in 2012. 20 years down the line, will the same sediment characteristics will be there or not? No. Fines may increase. So fines may increase, then what happens? Your design goes haywire. Got it?
There is no solution to it. We don't know what's going to happen after 20 years.
See, okay, you are very pertinent question that you don't know what will happen after 20 years.
Yes, so we have to design as per today's condition if we are designing a project.
Not at all. No. We should see your structure is there for perpetuity. Tomorrow, you need to do a sensitivity analysis of your settling basin considering the future sediment characteristics.
How to work out?
Yes, how do you work out? Suppose today you have 40, 50 and 10. 40 coarse, 50 medium and 10 this thing. You design your sediment basin with 70, 30, 10. Like this, you go on changing your first this thing and see what happens to your system and how much goes to turbine. There's a live case wherein the fines have increased significantly over last 30 years. But the way you design is different. Today the efficiency is different. Even the project developers don't know that. I have to tell them that your settling basin is underperforming, not optimal performing. Why? Because the characteristics have changed. Maybe your course has increased tremendously and your basin is not performing properly. So these are things which.
So I have to add this thing. While preparing the guidelines in 2019,
Yes.
during the course of 2014-15, we come across a Nazoki's paper.
Pardon?
Paper written by Nazoki.
Yeah, Nazoki's paper, yes.
Yeah, on the sedimentation aspects and how it is going to influence on the hydropower projects or turbines. In fact. So there, Nazoki has come out with different graphs of the different aspects of the sedimentation aspects, where the head and the particle size gradation and the petrography all comes into the picture. So Nazoki comes with the loading arms or sediment arms, which is affecting the turbines. That was the main criteria for deciding whether descending basin is required or not, instead of the ppm itself. So the finer the particles, they are going to less harming. And the particle sizes are higher and the petrography is towards quartz or something else, it is going to more harmful. So accordingly, he has classified. So it is not directly working on our Indian rivers. That's why it was not included in the 2019 guidelines. But it is also give an insight that not only the ppm that going to harm the turbines, it is the particle size which is going to harm most, and the petrography. Those aspects are also.
Absolutely, you're right. Nazoki's paper is telling that the entire gamut of the sediment characteristics, that is the concentration, the particle size distribution, and the petrography, all are important. And it comes out with a what we call how many hours of turbine will be running if you are injecting this into the system. Got it? Now, again, Nazoki's paper is based on around 16 to 20 cases.
Yeah.
Okay. Okay. Now, today, if you as I'm giving some food for thought for you people for tomorrow, you take out all your projects. You have around 20 or 25 desilting bases which you have designed. Go to the river characteristics and find out the river characteristics. I myself have seen the petrography has gone, quartz particles have gone from 36% to 77%. Now, what do you do with that river? Got it? Nazoki is fine. He has published some based on international projects he has published. But the effect of seriousness of sedimentation, which is in India, cannot be compared with anywhere, India and China for that matter. So take out your 25 settling bases. We have done a lot of models.
Going through some data, we have worked out a lot of these aspects, and we have found that in Indian rivers, we are mostly 15 to 20% only the coarser particles.
15 to
15 to 20.
coarser particles.
Yeah. So remaining is the fine and the medium. Finer is the 60 to 65%, and the medium is in the range of 25 to 30%. So in our case, the dissenting basin is not as such required if the ppm is also highest. That's why in 2019 guidelines we have included that the reservoir health as a settling basin, and we should introduce sluices and other things. So accordingly, classification has been done.
Yeah, I saw that 2019, but then I will not say anything. But right now, there are certain things which needs further addition to that. I think in the subsequent version of that, we would like to add it. Again, in the numerical modeling, it has totally underplayed the numerical modeling, which is a concept at all. I was asking you what sort of a design we do. We do empirical design. What we do is empirical design, either Masonic design or use any of these things, and then we go for model study, and then we go and implement it. I want you all to really go into the CFD analysis, CFD modeling of that. That is very important now. And if you do a CFD modeling of that, you have numerous models for that.
But again, in CFD modeling, while we are assuming the bed load, it gives a lot of changes in the results. While we are getting 15% or 20% or 25%. In case of Brazil also, when we are getting the studies through the DHI, in case of the ongoing proceedings in the US authorities, we have done a lot of iteration with the changing the bed load pattern. Because a lot of scenario has been changed drastically. So numerical studies give you a lot of results in front of you. You have to take the decision based on experience only.
See, bed load, I understand your point. Bed load is something for the reservoir only. Bed load doesn't go into my settling basin. Bed load doesn't go into my
Bed
settling
load also
basin.
contains certain part of the finer bed particles. Bed load as a whole is not only the coarser particles, it also has its sedimentation distribution curve. Unfortunately, we are not having the sampling and other aspects, we are not having much data regarding the wet load.
See, what basically I'll tell you, most of these things now are into the numerical because you are assuming a bed load. You are assuming 5, 10, 15, 20 and do the analysis. But can any physical model do all this analysis? No. You cannot do anything sitting in Delhi, you cannot do anything on your desk because it's not just an empirical design. It's not just mere empirical design. What you do, Masoni is only you get some dimensions of that. But then the entire geometry of it to increase the efficiency of the basin, you need this models to run. And that's where we need to have dedicated people who run these models for the reservoir as well as for the settling basin. As you said, the bed load is a major factor in the reservoir sedimentation studies, not on the what is going into my intake is only maximum the trash rack size.
I agree. But we are observing the raising in the beds due to sedimentation aspects in the reservoir in front of the intake. And based on that, the prediction of the sedimentation at the different levels has been arrived at by the DHI. So this scenario has been, so what was the in front of the intake that we are assuming that is going to hit the turbine. So based on that, we have taken the different aspects and the results get drastically changed.
I'll tell you. Now there is a very interesting thing. When the Paglia was being contested in 2005, 6, 7, I think I'm going deep into this subject, but then the curiosity I'm answering that. When Baglia, India-Pakistan thing was going on in Baglia, they were not interested what is in front of the intake. We had some channel in front of the intake and we were saying it's going through the bottom outlets. Got it? They were interested in what is the particle size which is entering into the turbine. In 2006-7, we didn't have any capacity to answer that question. I still remember the model which we ran in 90s in Norway. Me and subsequently Arvind Agrawal also did it. We together worked on it because Naresh Kumari, Jasna, everybody knew that we had run this model. So now the question of the neutral expert was, what is the particle size which goes into the intake? How do you do that? Either you do through a physical model study. Even here, they only measure what is coming out at the end. They take the thing and do the particle size distribution. That is one thing. Or you do it through a numerical model. What we did was we simulated that Bagliar case. In the phase of the intake, what are the particles which are entering into those cells of the intake? We added that and said that now because of our thing, we are getting this much ppm of sediments going into this. Now if I raise, as you said, if I raise my bed below this entry also changes. More will go. Moment the bed comes till the sill level,
More and heavier
everything will go.
More and heavier will go.
Heavier up to the size of the trash rack spacing, not beyond that. Trash rack spacing is the limit, got it? So, if I raise my bed, I get more into this. If the bed level comes up to the sill of the intake, everything will go into this. So, that's where I say that we need to have all the iterations to be done for the reservoir and for the settling basin. And that is what could answer the Indian side that this much sediment ppm is going. But for this, we didn't have any numerical modeling then. But I still want that more and more people work on this so that you can play with the system. You can change the reservoir for bed levels. You just see how much goes into this thing and try to play with it. That's only my message here. Got it? Very nice. So now, I think there is a level, there is a break, no?
Yes, yes.
Okay. So we move to other things subsequently, okay? After the break, in 15 also we came with a advisory document also on the glacial lake outburst flood. So technology is always evolving. That is always you have to keep in mind. Not that your predecessor did something was wrong. In 1985 क्या हुआ था मेजर चेंज, फ्लड चेंज हुआ है, आप लोगों को याद हो 1985 के BIS कोड जब आया है, ब्यूरो ऑफ इंडियन स्टैंडर्ड कोड के, व्हाट आर द मेजर चेंज? 1985 तक हम सिर्फ स्टैंडर्ड प्रोजेक्ट फ्लड लेते थे, उसके बाद PMF आया उस पर. So people who did earlier dams before 1985 with standard project flood, we won't say that they did wrong. The concept of PMF was not there. Got it? So subsequently PMF was introduced, and if you test PMF on the older dams, they may not be safe. Now what has happened is, we were talking in 2005-10, we were talking about it. After this October 23 Sikkim disaster, GLOF has become an integral part of our design now. He said PMF plus GLOF, am I right? That is the concept now. So it doesn't mean that people who did PMF are wrong. No, we didn't have even the idea of that GLOF would be so disastrous. So हमारे पिछले successors and predecessors थे, post independence, they did their best possible thing and created. But now nature is giving us some new challenges, that is glacial lake burst, which is not accounted for. We used to take the worst case, PMF or GLOF, but then PMF plus GLOF आजकल शुरू हो गया, तो which gives a different spillway capacity and water that is required. So technology is always evolving. Now urban flooding, we were only worried about the riverine flooding and all, but what happens to urban flooding now? CWC has moved into from riverine flooding to urban flooding after the Uttarakhand disaster, then the Srinagar, then Chennai, then Kerala, then the Ganga. So lot of flood studies our engineers have done, and with this last 40 years of Dam Safety Act efforts, the act has come. And now you see a lot of dam safety is a buzzword everywhere, not only in the center, in the states as well. So the hydrological review, what I was saying, many dams may not pass the hydrological test because they were all designed with SPF. Structural reviews, fine. Hydrological reviews, operational safety. Again now comes to the hydromechanical things. I have been in some of the committees where I see the hydromechanical gates and walls are so dilapidated. I mean, in the wire ropes have got, अब wire rope का जो है, अगर आपको wire rope को check करना है तो कैसे check करते हैं आप लोग? Anybody from HM here? Gates. If you want to, you can see the dam structure here. How do you know really that ropes are of adequate diameter and this thing? So you have to see whether the ropes which were installed 40-50 years back, so whether those ropes of the gates are intact. There is a technology has come for that also. So like this, new and new technologies are evolving for everything now. So that this dam safety ecosystem has brought a lot of new things into forefront. Basic facilities हम check करते हैं, basic lighting, roads and all those things. Now, comprehensive dam safety evaluation is also one of the key things, which as per the Act one has to do before December 2026. Dam break modeling is something where it's an entire event. Now, what is dam break modeling? You all of you know what is dam break modeling. But this dam break modeling is one word doesn't complete everything. It is what we need to do. We need to do the hydrological modeling. ऊपर से रिवर्स में क्या आ रहा है पूरे कैचमेंट को मॉडल करिए, डीएम डीटीएम लीजिए, उसको मॉडल करिए. मेरे रिजर्वायर में व्हाट इज कमिंग इनटू माय रिजर्वायर, दैट इनफ्लो फ्लड हाइड्रोग्राफ आई हैव टू डेवलप, एंड देन व्हाट इज द फंक्शन ऑफ माय रिजर्वायर इन अटेन्यूटिंग द फ्लड, एंड व्हाट इज द रिजल्टेंट पीक व्हिच इज गोइंग इनटू दैट onto the dam body. So how much my reservoir is going to take it, that is my reservoir routing, and then I get my flood which goes into the onto the dam. That is now going down. That is what will be creating the flood downstream if it breaks. Now what can be conditions? It can have overtopping of the dam, dam can overtop, dam can have piping. Even if your normal conditions, you can have uncontrolled discharge from the dam. over the years what happens, like in the Damodar Valley Corporation, the downstream river stretches are all encroached upon. So even if I normally discharge, so the design discharge I live, I see people are affected and people. So there are various conditions on which you do that. Based on that, you do a modeling scenario flood inundation map of all the areas for various cases of piping, controlled reservoirs, release, and then for overtopping. Whether it is a man-made dam or a concrete dam, and then you draw the flood inundation maps. उसके बाद आप क्या करेंगे? कितने लोग affect हो रहे हैं उसमें? You find out the people affected and who can lose life, because some people cannot be saved because just downstream में बैठे हैं, पानी आया तुरंत गया, वो लोग तो गए. जो जहाँ पे आप कुछ डिस्टेंस पे हैं जिनको बचा सकते हो, you have the evacuation plan. So what is happening in this is, we are internationally, what is happening, I'll tell you. Internationally they have a model which does the HNH modeling. HNH modeling is for the upstream part. Then they have the dam break modeling. Dam break modeling आजकल हैकरैश में हो जाता है, ठीक है, dam break modeling. Then they have the evacuation plan and emergency action plan. So तीनों के सॉफ्टवेयर अलग-अलग हैं उनके पास. So they do this, then they feed into this. After this breaks, they go and to see that how to. वो जो हमारा emergency action plan है, that has to have a synergy with your disaster management plan, DMP. हमारा Ministry of Home Affairs has created DMPs for every district. अगर आप उनके साइट पे जाते हैं, उन्होंने every district they have created one DMP. That is for fire or for accidents or for earthquake or anything like that. That flood also has to go into that. And the communication routes from the dam authority has to be integrated into that. So this is the entire chain of activity which encompasses into this dam break modeling. जिसके नीचे आगे लिखा है मैंने अपना flood inundation mapping and emergency action plan. So this is how you classify the hazard potential of every dam. So. And then of course we have many other things which have come up now. I think I have discussed this glacial lake outburst flood. Now let us come to some case studies now. I heard whatever I told you so far is all covering various aspects of this. Some of these I might have left it, but because of time constraint. But then I thought, let me go into one or two case studies where you can understand how we handle the complex cases which come across to you. I think some of you were involved in this one or two cases, so you may be aware about it. But then for all of you, I'll tell you how we really handle such challenges when it comes to you. The case study one, which is something which is an engineering failure, and let's find out the cause and evolve a solution for a failure of a penstock bifurcation sickle plate. ये केस CWC के सामने करीब 2000. When did you join?
2009 sir.
It came around 2009 or so. It came to CWC. Anybody else who knows about this case? No. So. This is something which is a lesson which one should really understand, because it has gone through a lot of exercise by including many stalwarts of CWC, starting from Mr. Jayasilan, Mr. Naresh Kumar, Mr. IIT, Metro Delhi, other people who are there, Mr. Patel. So first for what is bifurcation? Bifurcation is something where a water, when it's flowing, it bifurcates in the water conductor system in the penstock. In this case, it is a 15-meter tunnel, then goes to 12 meter, then it goes into 9, then each one is 6-meter tunnel which is going to the powerhouse. So 1, 2, 3, 4, 5, 6. We have 6 penstocks which is entering into the powerhouse. So bifurcations are required to split or divide the flow in tunnel or penstock for feeding water to multiple units of hydroelectric facility. So now you can see there are 4 bifurcations. Is it clear? 1, 2, which are circled here. There are 4 bifurcations that water is bifurcating into 2. Once you have a bifurcation, what happens is unbalanced forces are generated in a bifurcation. The moment you are cutting a pipe and making it like this, you are having some unbalanced forces at the junction of the pipe. Here, how do you manage these unbalanced forces? You try to strengthen the junction by either an internal sickle plate or an external yoke girder. When you have an underground powerhouse, you don't have space outside the bifurcation to strengthen it. So what you do is you strengthen it internally by calling it as internal sickle plate. What is sickle plate? Is a thick plate, and we calculate the forces that can balance the unbalanced forces which is trying to pull out the bifurcation. So the strengthening member is internal sickle plate in the instant case. Now you can see from the inside of the penstock there are two penstock coming, and at the junction you have the internal sickle plate. Now this is around 62 millimeter thick. In another case we have around 82 millimeter. I told you there are four bifurcations. Two are 62 mm, two are 82 mm. If you want to know the size of this with respect to a human being, you can see the size of the sickle plate and where is it. What is the size of this? Because the diameter is 9 meter to 6 meters. Got it? One is from 12 to 9, other one is 9 to 6. Now what you see here, you can see some horizontal joints, welded joints in this. Can you see that? Yes. Please note that when useful for further discussions, you note that we have a horizontal joints in this sickle plate. Now, if you draw a sickle plate in a graph sheet, this is the whole thing. You can see the end, towards the end it has broken. This is the one part in one day, in October 2009, somewhere it happened that this piece was found in the spiral case. And another piece which was found in the power penstock was this one. These two pieces have broken and they have gone to the penstock, to the spiral case. Near the stayways they got stuck up. They have broken from the horizontal bed which was provided in this. In the other bifurcation too, you can see this one came out separately, and this one was the second portion which was found in another unit. So far clear? Any doubt? If anything not clear, just let me know, because subsequently I will be discussing further details. Now you can see all the horizontal joints. Now the end result is something like this. You don't have a sickle plate. You can see the remaining sickle plate at the bottom, and you can see the remaining sickle plate at the top. You want me to point over there, or it's clear? It's clear, no? So the remaining sickle plate at the bottom and the similar sickle plate at the top. Now what could be the probable reasons of failure? Now I leave this to the floor. Let me tell, each one of you can tell what could be the probable reasons of failure of this sickle plate. Now water is flowing, then it goes in two directions, and then you have failure of the sickle plate in this fashion.
Failure of joint.
Failure of joints. Very good. That's number one.
Dia of one outgoing pipe may be larger than the another one. If that is the situation, then maybe some differential pressure.
Differential pressure. Oh, good. Next.
So angle of placement. Angle of the sickle plate with respect to the flow.
Angle of the sickle plate. Okay. Okay, fine.
Fatigue.
Angle of the sickle plate normally we give to balance it in the direction to balance the force, the resultant is becoming zero. Okay, anyhow, that can be a misalignment of that, what you say. Fine, next.
Fatigue. Fatigue due to repeated
Fatigue due to repeated,
plus and minus.
it is a pump storage plant. This is a Srisalam is a pump. I forgot to tell you about the word fatigue. It's a pump storage plant. You have the flow in the forward direction, also you have the flow in the reverse direction, because Srisalam all the 6 units are reversible turbines and pump storage plant. Yes, fatigue. Next.
Poor workmanship.
Poor workmanship. Okay.
Resonance?
Resonance.
Some
Yes.
kind of cantilever action might be there in the reverse flow in the other direction. This is the depth.
Cantilever action in the, okay. ठीक है.
Sir, because diameter is of circular shape, and hook stress might have been generated instead of longitudinal stress. So, if the welding instead of horizontal welding, it could have been vertical welding, तो इसमें failure का chances और कम हो जाएगा sir.
Good point. Yeah, that's a very good point. Next. आजकल कहाँ हो पापा जान?
Correct है sir.
फर्क कहाँ है? अच्छा अच्छा, आप कहीं और मिनिस्ट्री से ट्रैवल करके अच्छा वहाँ चले गए?
Yes, sir.
Next.
Actually, that joint may have designed for shear, but there may be a tremendous bursting pressure. Due to that joint failed, and huge tension might have generated.
Fine. See, now whatever you said, anything could be there. Now when you start this, the problem comes to CWC and how do you start it? CWC has, prior to this, designed more than 100 bifurcations in the country, starting post-independence, and all are standing fine. We designed a bifurcation, yes?
This was of a larger size than all other sizes, no sir. The prior sizes were smaller bifurcation piece, whereas this is the largest bifurcation piece which was designed in CWC.
Fine. So you know the matter, so you know the case. So point is now, what happened is we have designed more than 100 bifurcations as per the established design procedures, what we follow and what has been coming from our people earlier who have designed all these major projects in the country. That is something called the texture-wise formula we use everything and go ahead and design and issue the drawings. Now, same thing was done in this case also, and it happened 7 years after the failure happened after 7 years or 8 years of the commissioning of the project. Now, the probable reasons of failure, what all you said, could fit into one of these categories. It could be metallurgical issues. The plate was having incomplete fusion. Plate itself would not be proper, number one. Design could be faulty, or unforeseen factors have not been taken in the design. Fabrication issues, site welding issues, and the way the units have been operated also could be the issue. So these were the various possible causes we summarized that, these could be that, which category this problem fits into this. CWC cannot handle that or could not handle it individually because we didn't have the expertise to address this issue. So, who will do the finite element modeling? That time we had, among CWC, we had Rekha was there, who had come from G. Yeah, G, and she was able to do ANSYS. But then that time we didn't have so she did good amount of ANSYS studies. But then we wanted somebody from IIT Delhi. We inducted Dr. Patel into that. Then we had, for the welding aspects, we introduced Iyer, Welding Research Institute. AP Genco was the parent body of the CA for the operation procedures. For the material part, National Metallurgical Lab Jamshedpur was called. Then for the measurements of the vibration and all those things, Fluid Control Research Institute Palakkad was called. And of course, we brought in international expert Harza also into picture. Because such a large size of bifurcation was never done. Internationally, we saw there was no such failure at all on a bifurcation at all. So we didn't have a case study to really solve it, how to solve this problem. We always go by precedence. If somebody has done somewhere something, we try to see, okay, how we can do it. So finally, all these people were taken into this thing. IIT Delhi did the CFD modeling of this into plant profile, and the isometric view is given here. They ran the entire thing and they studied all the bifurcations. On either side of the bifurcation, what are the pressures getting developed, and what is the flow pattern, where is the flow recirculation happening. And with this was done by your colleague here. She, remember these slides? Yeah, this was done on ANSYS based on various criteria which was developed then in 2009-10. Yes, now here I stop it. So basically what happened was, now you may say, well, what is the final conclusion of this? We got the material tested at the National Metallurgical Laboratory at Jamshedpur. We had sort of a sulfur segregation in the metal, in the plate. What was used in the plate of the sickle plate, we had sulfur segregation, we had incomplete fusion. But these are, what I am telling all these are the things you need to see in the future projects when material test comes to us. Normally we don't see the material test, whatever comes to you, design and give it. If the material is faulty or something, some problem is there, some defect is there, and something happens, the problem comes to CWC. So metallurgically we saw there was incomplete fusion, we had sulfur segregation in the metal. As a result, there was some flaw in the metallurgy of the plate. Sickle plate fabrication issues, I'll come to design later. Fabrication issues. Normally when we all issue the drawings for anything, we leave it to the agency for implementation. Now coming to the steel structures, you all should see that the fabrication drawings also come to CWC, because if you have designed everything properly but the fabrication is like they put horizontal joints where the stresses are maximum, your weld is going to open up from there. So as one pointed out that the horizontal joints were the culprit. So please ensure that once you issue the steel drawings, the fabrication drawings also come to CWC, and after this I was insisting that the fabrication designs should be seen by CWC whether the welds are properly given. The weld should not be the way it was given in this case, because these are the most dangerous welds which was given here. The maximum stress is occurring at this area. The maximum stress is here. So all these get opened up over the time. So never give such horizontal welds in this. So the fabrication drawing should essentially come to CWC, and we should see that it is compatible with our design.
But sir,
Yes.
If the welding is done like that, even in case of hoop stress, it's the tension, and the welds are designed for tension. Here also it's coming tension, so it should have been designed. अगर वेल्ड ठीक से डिजाइन किया है और ठीक से साइड पे हुआ है, then I think that should not be an issue. क्योंकि हुप स्ट्रेस में पूरे स्टील लाइन में सब जगह टेंशनली डिजाइन होता ही है सर.
Yes, बिल्कुल आपने सही कहा है.
सर लेकिन लॉन्गिट्यूडनल स्ट्रेस और हुप स्ट्रेस में सर, जो अगर हम सिलिंड्रिकल वेल्ड की बात करें तो हुप स्ट्रेस इज ट्वाइस द लॉन्गिट्यूडनल स्ट्रेस. तो कभी भी जो डिजाइन है उसमें हॉरिजॉन्टल वेल्ड इज कैटरिंग टू द लॉन्गिट्यूडनल स्ट्रेस, नॉट टू द हुप स्ट्रेस. तो ये फेलियर तो हमेशा रहेगा सर जब हॉरिजॉन्टल करेंगे. अगर इसको वर्टिकल करते हैं दैट विल बी टेकन केयर बाय द हुप स्ट्रेस. हुप स्ट्रेस उसमें वर्टिकल जो वेल्डिंग किए हैं उसको वो टेक केयर कर लेगा. ऑफ कोर्स दोनों में टेंशन में डिजाइन होता है, लेकिन हुप स्ट्रेस का मैग्नीट्यूड ज़्यादा होता है हॉरिजॉन्टल से, और हॉरिजॉन्टल वेल्डिंग करने पे हुप स्ट्रेस कैटर नहीं होगा सर, उसे लॉन्गिट्यूडनल को करेगा. इसलिए वर्टिकल वेल्डिंग करना उसमें जरूरी था.
और वो जो प्लेट जा रही है, अगर वर्टिकल वेल्डिंग ये प्लेट यहाँ जाके वेल्ड होगी ना,
ऐसे ऐसे
ये वाला टेंशन तो आ नहीं है.
ऐसे ऐसे
हाँ, ये वाली हमने ऐसे वेल्ड किया, उसके लिए ऐसा वेल्ड किया, तो अल्टीमेटली ये तो यहाँ वेल्ड होना ही है ना. अगर ऐसे में वेल्ड होगा यहाँ से कर लेगा, अगर वेल्ड ठीक से नहीं किया.
गुड, मुझे बड़ा इंटरेस्टिंग लगा कि आपके सवाल का जवाब उन्होंने जवाब दे दिया आपको कि सी स्ट्रेस इज वन थिंग एंड लॉन्गिट्यूडनल स्ट्रेस इज अदर वन, एंड इफ यू रियली डू एफईएम मॉडलिंग, हमारी एफईएम मॉडलिंग के बाद हमने जो स्ट्रेसेस यहाँ निकाले थे इस पे, जो आईआईटी दिल्ली के स्टडीज पे, इट वाज समथिंग व्हिच could not be taken, and that's why it started opening, those joints started opening. Had you given a stiffener over that, things would have changed. Got it? Got it? So your query has been responded by him in the sense that there are two things, hoop and longitudinal.
Now critical case क्या बोला?
हाँ जी
While
बताइए.
pumping और while turbine वाला.
Yes.
Pumping भी different units के साथ combination के साथ कोई है?
एग्जैक्टली आपने अभी मैं आ रहा था उस पर, आपके पॉइंट जो है बिल्कुल, अगर लास्ट पॉइंट इसमें जो है ना वही इसी पे आ रहा था मैं. सो ये तो हो गया बिल्डिंग का इशू. बाय द वे इस कमेटी में करीब 8-10 लोग थे हम लोग, एपीजन को, जैसे साहब, मैं, नरेश कुमार जी, हमारी पूरी टीम थी, सीडब्ल्यूसी के राकेश टोटेजा, he was there, and then IIT Dr. Patel was there, then Mr. Jamshedpur के this thing Welding Research Institute, everybody it was there, and APGN को के सारे top pros थे उसमें, but so everybody had their collective wisdom pouring into this. So sickle plate fabrication का हो गया, site welding is another thing. Now during these are 62 mm thick plates, stress relieving की जरूरत पड़ती है. So 62 mm stress relieving में what all things happen, that is a separate thing which is another issue in this. Coming to the unit operation procedures. This is operating, normal flow is happening, absolutely fine, water gets bifurcated and goes. But what happens when there is a turbine pumping of this? When the pumping of the turbine is happening, there is the worst condition is on the pumping phenomena. The differential pressure was found to be more on the pump cases than the generation cases. G cases and P cases. But P cases were more damaging because of the differential pressures which is happening on either side of the plate. So it gives sort of vibration also. We presume that. See, हमने किसी ने फिर हमने
ये cycling loading होता है.
It's a cycling loading. Okay. Once cycling loading comes, it's a fatigue phenomena. Okay. अब बताइए, हमारे जितने डिजाइनर्स हमारे यहाँ बैठे हुए हैं, जो लोग सब्जेक्ट मैटर से इंटरेस्ट रखते हैं, we don't design a bifurcation for fatigue loading. Never in the other projects we have gone into fatigue conditions like this.
Pumping mode में I think this was the first one.
पंपिंग मोड में और भी प्रोजेक्ट्स हुए हैं, बट द ज्योमेट्री इज नॉट लाइक दिस. इसके पहले 4-5 और पंपिंग स्कीम्स आ चुकी हैं. आपको इसकी लेआउट बताओ जो आप लोगों को फ्यूचर में आपने आगे के प्रोजेक्ट्स में भी देखना है क्या करना है. यू शुड नॉट अडॉप्ट सच सम ऑफ दीस इश्यूज फ्रॉम हियर, लाइक आपका जो ये साइजेस है, मोमेंट यू हैव लार्ज साइजेस, go for a complete bifurcation, number one. When you have large sizes, don't go for this sickle plate or external, you got to go for a complete bifurcation, which we did in the top. ऊपर सबसे 15 से जब 12 हुआ तो we made it a complete bifurcation because इतना बड़ा sickle plate कहाँ देंगे, और complete bifurcation पे हमें AFC जर्नल में मुझे पेपर मिल गया था, तो हमने उसको कॉपी मार दिया इस पे और लगा दिया इसको, उसमें कुछ नहीं हुआ. complete bifurcation has no steel component at all. It's number one. Number two, never go for large size bifurcations of 9 meter this thing. Try to minimize it. अगर आपको compulsion है, so then what you do is you don't try to distance it from the powerhouse cavern. Make first of all, particularly in the pumping case, keep it away from the powerhouse wall. Don't make it 30 meters or 40 meters from this. You try to distance these bifurcations away. Number one. Number two, between two bifurcations, try to maximize the distance. Don't try to make it as close as possible because the flow of one bifurcation goes and interferes with the flow of the second bifurcation in either way. Got it? So, हमारे डायरेक्टर जयसलन साहब थे उस टाइम, बट देन what happened was Jayaslan Saab, Naresh Kumar, all of us, we were doing, none of us had gone for that fatigue calculation because we in CWC never do fatigue thing. That is, Harza brought this concept now.
But sir, in railway, we are often do this fatigue test for cyclic loading in railway bridges.
You are right, fatigue tests are done in many places. We do it.
For different cycles.
Absolutely. But as I said, we are evolving in everything in CWC. As a result, fatigue test studies were never done for any of these components. So bifurcation में something is called SN factor, S by N factor. SN factor का जो है वो हमें अब देना पड़ेगा आगे के प्रोजेक्ट्स में. तो तब से हम लोगों ने फिर सबको बताया कि SN फैक्टर लीजिए, जिसमें आपका फटीग अगर उस ग्राफ के हिसाब से इसके अंदर आता है तो आप इसको ये करिए, हमें इस तरीके से उसको अडॉप्ट करिए. सो बेसिकली then last was operation. So what design में जो है the fatigue angle was something which was missing, and then coming to the joints, the horizontal joints which were there were all removed, and what was the solution given? Now the cause was a mixture of everything, it was not only fabrication or it was a fabrication issue, it was a why? Because it was happening in the last, during commissioning stage this happened. Commissioning a date was given and all these things were going at a fast speed. So as a result what happened was, everything was going on, nobody is bothering, and finally we ended up into this down the line. But this has a time dependent phenomenon. It didn't happen in the very first running, it happened after 9 to 10 years of the operation of the plant. सो आज आप जो प्लांट बिल्डअप कर रहे हो उसके अंदर क्या डिजीज शुरू हो रही है और कब जाके कल्मिनेट होगी वो पता नहीं आपको. वही पता लगा ना, लास्ट वीक मुझे किसी पता लगा किसी पकड़वे में बहुत ज़्यादा पिटिंग हो रही है, तो देन आई गिव माय सजेशंस, बट देन व्हाट हैपेंस subsequently also is to be seen like a set for settling basin, similarly for the your components of the system. Now what was the final solution? I'll just briefly tell you that a plate was given along this side, additional stiffener was given along the two. Now that you cannot, in the existing one you cannot do anything, so additional stiffener was proposed here, and a new sickle plate was created with stiffeners here all along this thing and all along the junction. And that's how it has been done around 8 years back or so, and we have been asking them to run operations also on the pumping operations. We have given some restrictions there. This committee is a standing committee of TS Genco which meets, but then we have asked them to inspect it timely and give a feedback on the whole thing. So, but now the TS Genco, the entire brass has changed. They don't know the seriousness of this issue. So, पिछले 3 साल से they are not bothered about it. But then, people who are handling that in the current system of CWC should be able to understand that this is something which is there happening, and they need to inspect it so that anything on the solution, if has some defect or shortcomings, can be corrected. But it was running for 4 seasons. It was running perfectly all right. Initially we had given restrictions that no pumping should be done, then we increased to 50% pumping, and we said one can pump, other should, if you only pump, both should pump something, some conditions we had given them, so that there is no unbalanced force acting on this. But this example gives us a lot of learnings for future projects of this magnitude, because a lot of PSPs are coming, and I wanted to show this particularly because in PSPs these layouts are being copied and pasted everywhere. Got it? Because as of now it's only DPR, but when it comes to implementation to CWC, the designers have to be very careful in all these layouts. Now, I think with this I'll close the अब आप क्या देखना चाहेंगे? अब मैं एक अपना वीडियो चला रहा हूँ उस पर, ठीक है? ये बताइए, आपको पोलावरम का कोई लेक्चर हो रहा है इससे सेपरेटली? नहीं हो रहा, ओके। I'll show you this video. Just have a look at it. You can, first thing is you have to find out which is this project, and then after that I'll tell you the whole story. Okay? Which project is this? Farakka Barrage. What is the story? Can anybody tell? बताइए. Pankaj or Manish, who is that? What is this?
सर इसमें तो इरेक्शन हो रहा है गेट का, मतलब दो या तीन पैनल में आके फिर वेल्डिंग कर रहा है। अभी तो इतना ही। इसमें सर वो जो रिप्लेसमेंट ऑफ गेट हुए हैं उसमें क्रैक डेवलप हो रहा है सर हॉरिजॉन्टल गार्डर में, और जो होल बना हुआ है ड्रेन होल उसी के इर्द गिर्द से सर वो फैल रहा है। तो इसमें तो सर अभी सिर्फ इरेक्शन का मुझे दिख रहा था, हमको लगता है मोस्ट प्रोबेबली 22 या 23 नंबर गेट होगा, क्योंकि इसके बाद फिश लॉक है 25 गेट। उसका आप कुछ बताइए सर।
अब कॉन्ट्रैक्टर कौन है?
कॉन्ट्रैक्टर उस समय तो दो ही थे, STL PPL और टेक्स माइक्रो, जो पूरे गेट को रिप्लेस किया है सर।
अच्छा, आप 2021 में 2019 में मिनिस्ट्री में थे मेरे साथ?
हाँ सर।
19 में थे आप?
हाँ। नहीं 19 में नहीं थे सर।
आप चले गए थे ना?
Yes, sir।
ठीक है। ओके, ये जो है दिस इज इंटरेस्टिंग केस ऑफ फरक्का बैराज।
इमरजेंसी केस हुआ था वो है सर ये।
एग्जैक्टली। तो आप चले गए थे दूसरे मिनिस्ट्री में उस टाइम की बात है, अप्रैल 10th 12th की बात है। फरक्का बैराज का एक गेट कोलैप्स कर गया था। वहाँ के गेट्स में कुछ प्रॉब्लम्स हैं, वहाँ पे जैसे बता रहे हैं ऑलरेडी सम क्रैक्स आर देयर व्हिच इज डेवलपिंग, एंड 35 के हिसाब से शायद रिपेयरिंग हो रही है, फेसेस में हो रहा है। बट देन व्हाट हैपेंड इज वन ऑफ द गेट्स फेल्ड समवेयर इन मिड ऑफ अप्रैल। What is the significance of mid of April is that it is the treaty period. Treaty with Bangladesh is from 1st of January to 31st of May. So what happens is that you have a very restricted release of water based on an agreed treaty between the two countries. And with this failure which happened, what happened was 15,000 cusecs of water was flowing uncontrolled because of this gate failure to Bangladesh. So that time Mr. Saibal Ghosh was the general manager at the site. R.K. Singh was one of the directors, and others, two more were there, I don't remember them. But then issue became very serious. because the state government can very well throw the thing that we are releasing water to Bangladesh and not for West Bengal. Central government was very serious that what has happened now. So that was, this case is only to tell you that what all challenges can come to you and how you need to address it and what precautions you need to take for that. So it was a Saturday night when I got a call from secretary. I was Commissioner FM then, that I had got from Saibal Ghosh already the information, but then he called me, "Kya ho gaya bhai, bataiye." So I said this has happened, and I'll let you know in the morning what will be the force of action. Itne mein next day Sunday 3 o'clock cabinet meeting was called by cabinet secretary. Now it was between me and Saibal Ghosh to really do the crisis management. Saibal Ghosh, one of our accomplished barrage engineer then, who is no more unfortunately, but then he said that I have a spare gate. The Tex-Mex was working on that project and there was a spare gate. So then I said, you just work out with your team and tell me how many days it will take to this. We cannot allow this 15,000 cusecs to go, whereas as per the treaty is very, very less to be shared with this thing. It's a summertime, we cannot share it. So now he did a wonderful job and he came out with a time that I have a spare gate and my entire erection will take around 7 days to do it, and in 7 days I reinstall the gate under the flowing condition, because you cannot stop the water. Normally you lower the gate in balanced condition. Now it becomes an unbalanced condition. So what happens is then 7 days I took from him, then I had to brief secretary. Secretary said, okay, फटाफट एक PPT बनाइए, आप आ जाइए 3 बजे वहाँ पे. वहाँ पहुँच गए, then it was secretaries and all, they put the onus on commissioners and the joint commissioners only. So we, that time Mr. Sambaria was our senior joint commissioner who is still there. We went to this thing and we made a presentation and said that these are the things. We have one gate over there and bringing it to this place and all, it takes 7 days to. Then questions come, why it collapsed, this, that, all those things, that's a different story. Okay, fine, it has happened now. So within 5 days, we want the gate to be installed. So that is what was the final thing. So then I personally went to this place, sat there. Entire team was working for almost 18 hours or so in shifts. This gate was put in place, and then by the 5th day, Friday, it was lowered with additional ballast and all, and finally the gate was installed. So we lost the water for around 6 to 7 days to Bangladesh. Then the diplomacy on, as a Commissioner FM, I am also the JRC member also. So I have to talk to the other side. The other side was a friendly guy. He said, no, I won't spread this in the media anywhere. You do it fast, and I also will try to. The damage was mutually also discussed. It was controlled. Fortunately, the then government of Mamata Banerjee government also didn't, because the fear was always there that she would be attacking the center. So somehow the whole thing was accomplished in 5 days. Now, the things which come out of this is, wherever you have issues, always you need to have spare parts available because of any eventuality, whether it's Indo-Bangladesh or Indo-Nepal, in Kosi Gandak barrage or any of these places, we need to have spare items available always to run the show, number one. Number two, this project, the whole, when it was built in 1975, you could see a road, rail, and then you can see this barrage. There was no way to close the gate earlier. Those designs were done with bare minimum cost. Post-independence, if you remember, you may not be aware, what we used to have, our seniors used to tell us that we used to economize on everything. Wherever there used to be one gate for service gate, there was no stop locks given because it was extra cost. India didn't have that much money to afford a stop lock gate for anything. Similarly, in this case, we had stop block gates, but we didn't have a walkway to inspect this gate. So during 1 year before that, when this Ashish Paul was the person in charge at Farakka Barrage, the walkway was built completely all along. You see where people are standing and working on the gate. So Dr. Amarjit Singh had pressurized Farakka Barrage project that, and I had told them that without walkway these gates cannot be inspected. People are finding a lot of difficulties, road, railway track, and then going to the gate is very difficult. So any barrage structures for that matter should have a walkway near the barrage so that we can maintain and the gates. So the walkway was built just 1 year back, the entire walkway. That helped us into this erection procedure. Otherwise, it was near to impossible to really do this task. So things are to be thought ahead of times, what happens when it happens. So today's we have enough of resources, financial resources, so we should think all these future problems for maintenance which can come across. The matter was solved, but it had its own difficulties. 5 days, anything could have happened. So tensions were always there within CWC and within ministry, and finally all this had to be borne by all of us only. The highest paternity only looks towards us. They don't have anything to advise you because they can only tell us directions, they give directions to you. But then achievement and accomplishment has to be done by all of us. So whenever you are planning a project or something like that, think of these things. Spares are very important for any component. I have numerous cases of rehabilitation. Fortunately, I had a lot of troubleshooting exercises to be done in my career. So every troubleshooting exercise gives you some lesson. Whether it's a penstock bifurcation buckling case or whether it's a flooding case or anything, you should have enough spare parts. If there had been no spare part, you can imagine the plight, getting a gate, fabricating it, bringing from some workshop, doing it, 1 month of my whole thing would have gone. So that is in brief the lesson which you had, the challenges which was faced here.
Sir,
any query on this now?
Sir, the message I got for the spare part and looking at that is okay. But I just want to discuss on the other aspect. You told that 15,000 cubic was uncontrolled, it was going. But the amount during that period, roughly 60 to 70,000 whole inflow is received. And anyway, Bangladesh was allowed to get something around 25 to 30,000 cubic during those periods, I think in April. So in that context, what was the issue?
See, what I am saying 15,000 was is more over and above the treaty requirements. I am not saying this, whatever was going, see what goes in the treaty, if you see the leakages of Farakka Barrage itself, if add all those things, it's still is treaty amount, or it's more than treaty requirement. Okay? So if you add this 15,000, it becomes far more than that. So आधे से ज़्यादा पानी लीकेज से निकलता है हमारे वो ट्रीटी के अंदर. अब देखिए कितने गेट 108 गेट में आपके लीकेजेस बहुत है.
लीकेज मेजर नहीं है सर, जो
लीकेजेस मेजर है. हम लोगों ने वर्कआउट किया था कि लीकेजेस भी मेजर है, बाकी गेट भी खोलते हैं बीच में.
बट सर जो सिल्क फ्लशिंग चलती है कंटिन्यूस 24/7 वो ऐड होके ज़्यादा हो जाता है.
वो तो ऐड होगा, वो तो बिल्कुल ऐड होगा उसमें. जो पानी नीचे जा रहा है वो सब ऐड होगा उसमें.
अभी एज ऑन डेट वहाँ लीकेजेस ज़्यादा नहीं है. इफ द गेट इज क्लोज देन इट इज ऑलमोस्ट लीक फ्री काइंड ऑफ. बहुत माइनर है. पुराने गेट में हो सकता होगा पहले.
पुराने उस टाइम क्या है 35 गेट चेंज हुए थे, बाकी जो 70 गेट थे वो बाकी थे, तो सब पे जो है कुछ ना कुछ.
अभी तो सारे नए हो गए.
अभी भी जो गेट्स में कुछ क्रैक आ रहा है, आई डोंट नो व्हाट इज दैट रीजन दैट आई डोंट नो बियॉन्ड दैट आई डिडंट फॉलो दैट प्रोजेक्ट. ठीक है, चलिए. एनी अदर क्वेश्चन? ये कितने लोग जानते हैं? हाँ, ये तो आप, ये जो केस है ये तो आपको सबको समझना चाहिए कि जो है जो स्टेट गवर्नमेंट की जो कैपेबिलिटीज है, हाउ दे रियली बिल्ड द डैम अंडर पॉलिटिकल प्रेशर एंड हाउ इट लीड्स ट्रबल टू CWCA and DSA. This is 2022 August when I was chair of NDSA and member DNR, and NDSA was just evolving, and that's when this whole thing happened. Mr. Pankaj Kumar was the secretary, and then one night they called me saying that this dam is now collapsing, send a team. But then we sent a team to this project. By that time already the thing had started. So what is this? What did you see? Piping phenomena has been initiated. Ignorant of that, there are people standing on top of it watching this piping going on. Now, what could be the subsequent thing of this? Can you prevent this piping now? So, now, this is what you see on the right is the end result of it. Okay. So this piping was continuing, and then finally the entire machinery of the state authorities, state engineering chief, everybody was there, and minister called me at night 11:30, 12 asking what is happening. Then I gave him the feedback, and our team left immediately at the evening 6 o'clock. Mr. Tripathi and one more two of our NDSA who were in additional charge, all of them were additional charge. I think
Harish.
who?
Harish.
Harish, yes. Harish Umbarje, who is here at NDSA, and Mr. Vivek Tripathi, immediately we sent them, and we were on hotline, secretary, minister, this thing, and all of us, what is happening. Udhar se unke chief minister site pe the. Now this dam was built, it's an earthen dam. It's an earthen dam. You build entire dam and take it together like this. What the MP state government has done is they built half the dam and they have taken it up. I mean, that is the level of engineering excellence in the states, that half the dam of the thing has been taken up, remaining half was following behind, So as a result, पूरा क्रॉस सेक्शन बना नहीं, और ये उनको फिलिंग भी बड़े जल्दी से, प्रेशर था, पॉलिटिकल प्रेशर था, फिलिंग के लिए कर दिया, फिलिंग बनना शुरू कर दिया इन्होंने. Finally this piping started. Now once this piping started, seriousness emerged, and then इधर उधर अपना जो है, they started searching for experts, and then all of them together. One side there was the spillway was not functional, the other side was not, it was a very massive rock. This side they could see that okay, we can excavate the channel, so you can see the channel excavation happening on the left hand side, and then after that slowly they tried to excavate it, and the water started flowing, and finally the entire reservoir which was filled was evacuated, emptied, and there was minimum damage to the property and lives downstream. But it took entire machinery of state government, central government to stand there, and for almost 48 hours people were working on this. The chief minister of MP appreciated the efforts of our NDSA team, and our minister also was quite happy that this thing was sorted out without any damage. Now again, this is a case of engineering negligence. What happens is, as CWC or NDSA, we get responsibilities thrust upon us which is not the creation by us. People build such dams. After this, there are 3 more cases during my tenure which happened, and each one is a unique example of that the state governments have least bothered on the operation, maintenance or construction aspects of it. So it is the right time that the Dam Safety Act has come and we have all this ecosystem put in place. So otherwise you would have not many such things. Even now for initial filling of the reservoir, approval of NDSA has to be taken. The whole filling schedule, everything has to be inspected, the dam has to be inspected. So I hope down the line things would improve in the dam ecosystem. So this was about how to mitigate the distress situation which comes to you suddenly as a new case. You have to leave aside all other activities and work on this. So our team of Mr. Tripathi and Mr. Harish did a wonderful job, and so that's where our engineers are counted on this. Even IITs cannot do. They got IIT Rogi, but उन्होंने हाथ खड़े कर दिए. So that's where I looked at CWC achieve that excellence all the time in future also. Got it? Next. Time है अब इसमें लिखा था ओपन हाउस डिस्कशन. ये चल रहा है या ओपन हाउस अलग सा होगा? चल रहा है. चलिए तो मैं एक और केस लेता हूँ आपका जो है ये अपना इंटरेस्टिंग केस है. हाउ मेनी ऑफ यू हैव सीन दिस प्रोजेक्ट? You have seen. Okay, very good. Where are you now?
Sir, I am in AP and additional charge of director ANC collaboration. I am in PP1.
PP, you are in PPA. Very good. But जी आप कहाँ हैं?
Sir, presently I am Senior Joint Commissioner in SPR1 and Assembly Province.
So you have gone there, no? You have seen the site, no? Fine. चलिए अब इस पे थोड़ा सा ये भी इंटरेस्टिंग एग्जाम्पल है. You have 25 minutes, so I'll explain it. So this is the whole layout of the project.
इससे कुछ नहीं होता. ठीक नहीं कर पाता.
What you see on the top of it is downstream coffer dam. क्या हिल रहा है यहाँ हिलते जो है बंद हो जाता है वो. Then we have this spillway here. अरे क्या हो गया? This is a spillway of the whole dam. This is the upstream coffer dam here. Yeah, यहाँ पे other dam आएगा. Just Actually, I will cover this. I'll just continue with this. Basically, this project, this is the spillway. This is the spring copper dam. We have one spring copper dam here. This is the main earth come rockfill dam which is to come here. The river is flowing from left to right. I'll not go into details about this project. I'll come to the main issues. what are the benefits now also not to touch much. Basically, this is the whole project. Broadly, if I say this is the whole main structures of this project, we have a spillway. The river is flowing from top to bottom. We have the approach channel on the left, spillway, and then we have this earth cum rock fill dam, and then the spill channel, and then we have this river going downstream to Dhaleshwaram barrage. So this is the entire broadly the layout. On either side, we have the left and right main canals and other things. Now, the construction of the spillway was over sometime in 2021 or so, and subsequently the earth cum rock fill dam construction is the major challenge which is there. Now, broad components are spillway, 1.1 kilometers, then the earth cum rock fill dam in 3 gaps. Gap 1 is earth cum rock fill dam, 2 is also earth cum rock fill dam, and gap 3 is a concrete dam. Total length of the dam is 2.45 kilometers or so. And we have a 960 megawatt powerhouse that is done separately. That construction is going on, and we have left and right connectivity works are going on, and then other canals distribution. Okay, that's then because of the interstate issues, Odisha and Chhattisgarh, we have the protective embankments and related land acquisition. Lot of land acquisition R&R works are there behind this project. So the basic physical. Now you may think why, when the river is flowing from top to bottom, why the spillway is given on the left side and why the earth cum rock fill dam is on the main central path of the river. So that is first curiosity which comes, why it is the layout is such. So basically the geological foundation which was seen there, we had better conditions of rock in the spillway at a shallow depth, the location where the spillway is given. And then on the earth cum rock fill portion, we have more of clay, silt and sand and all. So, but then what happens to the hydraulics? Hydraulics, you are giving the Godavari river a big turn to the Godavari river because of this spillway. So, numerical model studies were done. So, physical model studies plus numerical model studies were done in CWPRS Pune, and they found that there are certain issues coming up in the left bank of the spillway. Yeah, left bank of the approach channel spillway. And same thing, they could see something in the numerical modeling as well, which was done here. In both the things were done in CWPRS. So then we had to then think of certain embankments, left bank abutments to be constructed, and lot of permutation combination was done on the this side of this particular spillway. For streamlining, the velocities which were coming onto this particular base of the spillway was very high, and even water afflux was very high. As a result, we had to see that how it can be streamlined. So these were run on this model, numerical model as well as physical model, and there is a design DDRP, which is a review panel which reviews the design of the dam, because as per the Polavaram Tribunal Award, Central Water Commission has to review the designs of the dam. So under that provision, Central Water Commission also is a major consultant for the dam designs, and there is a dam design review panel as well working on it. So CWPRS, CSMRS, CWC, TPAs, then we have this other agencies also are all working into this project. Now, being a huge earth cum rock fill dam, lot of seepage analysis was done by IIT Tirupati in this, and what all they had come out with was taken due care in the design process. Now coming to the whole construction methodology. I have talked about design, fabrication, maintenance. Now coming to the construction part of it, this case would be a good construction case wherein if you see the spillway is on the left of the screen, and then we have the main earth cum rock fill dam, which is this is the main earth cum rock fill dam which is filled. This is the upstream coffer dam and this is the downstream coffer dam. That is, you can see, if you want to see the gaps, there are hillocks and between the hillocks there are gaps. So gap 1 is one hillock between two hills, there is one gap which is earth cum rock fill dam. Again gap 2 is between two hillocks, and then you can see there is a gap 3 here. The gap 3 is a concrete dam which has been already completed and constructed.
Just a minute, sir.
Yes?
Please.
So now the challenge is with construction of this earth cum rock fill dam here, gap 1 and gap 2. Now coming to this whole figure, you have many things, many geotechnical things. Now again, the faculty where CWC is not that strong is the geotechnical ground improvement part of it. Now if you see, this is the upstream coffer dam. Below the upstream coffer dam, we have provided jet grout walls. The jet grout wall is serving as a barrier for the water seepage into the work area. Then we have the downstream coffer dam. Now along the dam axis we have sand, clay. So wherever sand is found, we have gone for ground vibro compaction techniques there. Then we have wherever the clay is encountered, vibro stone columns have been designed. And in between, wherever there is a diaphragm wall, on either side of the diaphragm wall, there is deep soil mixing. So these are the broad ground improvement techniques which have been proposed for this project. Now this is the entire cross section of the ECRF with the entire foundation of it being treated. Now what is the vibro compaction technique? Basically what we are doing is we are trying to compact the sand by use of vibro techniques so that the required or the targeted relative density is achieved in this. So that's how the sandy areas are subjected to the vibro compaction. Now coming to the clay areas, we are going for vibro stone columns where stone aggregates are being we are pumping into this, and the same is similar to the vibro compaction. We are going for vibro stone columns. And this is the entire bottom where you can see the farthest thing where we are trying to stabilize the entire foundation of the earth cum rock fill dam because of the virtue of sand, clay and other material being found underneath this huge ECRF dam. Now coming to the jet grouting which has been happening under the coffer dams is basically the way is schematic view of the jet grouting which has been done beneath the coffer dams, and the entire thing has been tried to make it impervious. The flow of path has been increased by this to make the work area of the dam water free. But in the instant case of Polavaram, we have gone only for vertical jet grouting. And this is the further jet grouting wall which you can see, which was built beneath the beneath the coffer dams, and it so happened that in 2019 there was a change of government in Andhra Pradesh, and one of the team of PPA had visited the project site. The coffer dam was built. You can see the coffer dam. Yeah, you can see the upstream coffer dam. You can see the upstream coffer dam was built, and then there is a gap here, and there is a gap on the other side also. What happened was during the inspection of the PPA team led by CEO PPA, then they found that there is a huge 80% of the thing is rehabilitation and resettlement of villages because of a huge cost of the project is going to that. Only 25-30% is on the construction, remaining is all for the R&R project. One of the village by the name Devi Patnam village was not rehabilitated, but that time our R.K. Jain was the chairman of CEO PPA, and he could see that along with the team, and then they had said that you rehabilitate the village before you close the either gaps of the coffer dam. So that year in 2019 they didn't close the either ends of the so that water from the upstream could flow downstream. But then Devipatnam village, which was under submergence because of increasing of the water level, it was asked to be rehabilitated. As a result, these caps were left in the coffer dam. Now, it so happened that in that year itself, there was a change of government in Andhra Pradesh, and then the contractor was changed. The then contractor was changed to a new contractor, and this entire process of reverse tendering and all those things, it took around 7 to 8 months. So no attention could be paid to the Devipatnam village, or as a result, nothing, no R&R could be carried out. The villages were there as it is. But then they kept on saying, sir, no, we will be just shifting them to a new place, and their houses get almost every time inundated, no issue. But then as a Government of India body and Ministry of Environment and Forest and Ministry of Tribal Affairs, all were against that, no, you rehabilitate them, and then only. So as a result, what happened was that next year also they could not close the gap. So the gaps remain. But now what happens? A river which is flowing through the entire width of the river, and suddenly you allow that discharge to go through the two caps, certainly the velocities are very, very high. It was only for one season. After the monsoon, it was said that you close the gaps after rehabilitating the village. Here in this project, PPA is just a sort of a regulating body or observer or directions, but actual construction is done by the Andhra Pradesh state government or the WRT. So we don't have a say on their day-to-day activities or on their decisions. We are issuing finances, we are issuing directions, we are issuing monitoring it. By the CA monitors the whole thing. But then the political dispensation was busy changing the contractor. The new contractor came, he was asked to change this thing, but then that monsoon of 2020 monsoon also came, and then it just went across and it damaged the either side of the coffer dam, and it also left lot of cover pockets in that. So major flood was in 2021. 20 also we could manage, but the 21 floods were a bit more serious. As a result, you can see these circular areas are all covered pockets, which happened all along the downstream of the. You can see this blue color are all covered pockets, and the diaphragm wall which was built earlier also got damaged. You can see the diaphragm wall, this area, entire area, the water, this was not closed, the water came here, all these covered pockets, entire thing, this blue color are all deep covered pockets, and the diaphragm wall which was built for the main dam also got damaged. Now, the erosion also went to such an extent that you could see whatever the designed dam cross section, you can see below that there has been a lot of erosion and the dam cannot be built. So as a result, all the things have to be started again. Lot of discussions were held in ministry, in commission and in PPA, other places, so that how to rebuild this diaphragm wall. Whether to rebuild it or only to repair the part of the diaphragm wall which was damaged. After a lot of deliberations, because the diaphragm wall was costing around 600 crores or so, now who will build the cat? If CW says so you build a new one, it is, everybody says it's a CWC decision. PPA says you build, so now it has to be tested. So what we got the geophysicist from NHPC to test this diaphragm wall. They did a geophysical testing for the entire diaphragm wall and found out where are the pockets of weakness in that. So now either you repair those diaphragm wall in patches, or you build one more diaphragm wall only in those areas downstream of it, or you build the entire diaphragm wall fresh. Now these were the three decisions, and each one had its cost value, starting from 300 to 900 crores of investment again, just because of this not rehabilitating the village and not closing the gaps of the upstream coffer dam. Now finally, after a lot of decisions and all, it has been decided with this new government which has come in to construct the entire diaphragm wall again. And Government of India is also now funding this entire diaphragm wall again. And another thing is, a coffer dam is built not for 10-15 years, it is built for the construction period only. Even the coffer dam also, we had lot of seepages happening from the coffer dam because it had already withstood for 5 to 6 floods. So now there has been they have built buttress dam, I think Manu can tell us better. They have built a buttress dam downstream of the upstream coffer dam, and now the water has been arrested. So the work in the diaphragm wall area at a particular platform is now going on. Water is still there up to some level, but they are now raising the platform and trying to build the diaphragm wall. Once the diaphragm wall comes, then the entire dam will start. But it's a tremendous, huge challenge, working in this project, and people who are associated with this can appreciate the challenges which earth-come rockfill dam or earthen dam really puts before us. As on date, being outside CWC, if I see, we don't have really people expert in earth dam or ECRF dam. Every day if somebody asks me also, I have 2 or 3 people, tell them you can contact these people. But otherwise, people outside, we don't have really expertise. People who are there, our seniors of Central Water Commission, they have even 80 plus or 75 plus. As a result, we are not able to really render, or verbal advice they are rendering, but they are not able to really move to site. So here, international experts have been called now, from 2 from USA, 1 from Canada, or 2 from Canada. So they are all coming. They are advising here, and the work is now moving forward. So this is again a challenge that in future, if we have such projects of ECRF dam and such a foundation of it's a terminal structure. Either if I build another one in terminal Ganga in India, or in Godavari or Krishna in the Delta area, certainly we'll have these challenges. Now these challenges we have to be ready. We are not ready. In my opinion, we have to really equip ourselves with a lot of experience. So that's another challenge which I thought I'll place before you. So with this, this is not the end of it. These are only a couple of things which I thought, assorted challenges and problems I gave you. But if you really have, if I want to conclude, I think you have not many challenges in the projects. If you can go through the list, you have the Natpa Dam slide, Puna Dam slide, Polavaram, Rampur there was a major landslide, slope stability problem, Parvati 3 is also famous. Then we have this TBM failures, Sardasaro we have the cracks in the walls, Natpa Jakri, we had many things. Natpa Jakri was an example for CWC. We had hot water springs coming at 60-degree temperatures in the tunnels, and handling 60-degree. The workers cannot stand on the face of the tunnel. So we never faced such a condition of 60-degree water temperature oozing out from the face of the tunnel. It was a new thing for CWC. The entire team of CWC officers who were working on Natpa Jakri also didn't know what to do with this. Suddenly at one face of one of the tunnel, hot water of 60 degrees steaming. The labor were immediately pulled back, and it was filling the entire, you can't stand in the hot water, and it was full of steam. So first of all, the safety of the labor was taken. It started filling, the water filled up into the adit. Now we wanted that entire water of the aquifer to drain out in the tunnel. Then after that only start the remedy. After that stopped, temperature cooled down. After that we went about these solutions. But then the water cannot be immediately brought from 60 to 20 or 30. Then we had to place lot of ice cubes. Lot of ice cubes were placed on the face of the tunnel so that the temperature gets reduced. Then we had to put lot of ventilators, fans as ventilators, and so that the fumes can be taken out of the tunnel. And then the labor timing was reduced from 8 hours to 4 hours. So labor will only be there for 4 hours, come out, next labor will go. So the timing also was reduced, and the thing was finally done. So we have we have methane gas phenomena. I don't know whether how many of you are aware. Methane gas came up in Ranganadi project. So if methane gas comes, what is the solution? You should be aware about it. So you need to read the past incidences which are documented many places. Okay, now last one. I think before that I will not. One important thing is about penstock issues. When you build a penstock, when you are building and fixing the size of the penstock, always be careful that a man can go in. Don't make a penstock which is as small that a man cannot even creep in. Why I am saying is because you need to really maintain it tomorrow. Particularly an underground penstock I am talking of. Surface penstock you can maintain, but if you want to maintain an underground penstock, at least keep a size, though it is coming out from some other considerations, but when given a chance to you, you try to see that a man can go, because there has been a case of buckling of a penstock in one of the project which we were handling, and the project came to us asking CWC that, sir, our penstock is buffled and water is going out of the adit. There is an intermediate adit, water is flowing out of the adit. They wanted to find out what is the cause of that water from the penstock is moving out of the adit and not going to the power. So then we could find out that this location where the penstock has buckled. Once its penstock steel buckles, water will go into that and go out. Concreting might have been poor. Now the more challenge was how to approach the site and repair it. So we need to have a manhole on the top. The horizontal bed, we have a manhole. We keep one particular frame ready for somebody to enter into that, go down with proper lighting, cut those plates, weld the new plates, come out. So that is the extent of work we had to do. But then that gave us a lesson that tomorrow we have more than hundreds of projects where penstocks are underground. If any of them fail, in buckling, how do you repair it? Got it? Even after surge tank also you should give adequate length of horizontal reach of the penstock. Don't give from surge tank straight away one bend. Give a horizontal reach, put a manhole over that. Only then you have any wall chamber over that, but you can enter through that and go into the penstock. So any structure you build, you need to see how you can really maintain it tomorrow down the line. Rest all is quite clear. I think I need not mention. So these challenges are quite interesting, and it will really make you bolder and stronger every time you face them. And fortunately, I have been handling not many of them, and even now post retirement also, I am fortunate to handle such cases which people often come for advice. Thank you very much. With this, I conclude. Any questions?
Who took the decision to build a separate diaphragm wall? Whose decision finally it was? Whether it was CWC's decision or ministries or PPAs or what? Because that is a significant cost that I recently started looking into.
आप बताइए कैसे आप अगर CWC में मेंबर दिया था तब कैसे करेंगे बताइए कैसे करेंगे आप वो डिसीजन कैसे लेंगे आप हिस्ट्री इन्वॉल्व होगी ठीक है Who is to fund it? Government of India is funding PPA. Polavaram. कभी कभी कुछ हालात ऐसे हो जाते हैं ना तो डिसीजन निकल जाता है जैसे इलेक्शन हुआ सेंट्रल गवर्नमेंट जो है टीडीपी भी डिपेंडेंट हो गई है और बिहार में भी डिपेंडेंट है ना मेजोरिटी के लिए तो ऑटोमेटिकली इस प्रोजेक्ट को भी तो पुश करना है कि पोलावरम आंध्र प्रदेश का मेन प्रोजेक्ट है और उसको आप यू कैन नॉट गो ऑन डिलेइंग इट earlier the decisions were going on but later when the new government came obviously state wanted that the project should move forward so it was a collective decision taken together along with the international experts इसमें पहले क्या था पहले decision was not taken to have a new one because government of India has to fund if CWC takes we are responsible if PPA takes we are responsible ministry takes ministry is responsible then what happened was इंटरनेशनल एक्सपर्ट्स को ओपन किया गया, उनको ये रिजल्ट आई थिंक आफ्टर दैट ओनली इफ आई एम करेक्ट बिकॉज इट हैपेंड आफ्टर माय स्टैंड
already taken by secretary and minister.
Yeah,
But
but that was
taken.
pardon?
POE opinion was taken, experts opinion.
Your opinion of this international experts.
Yes, yes.
Yeah. So international experts को opinion लेके this happened in 23 or so 23 or 24. So POE जो है international bodies international experts जब कह देते हैं, so none of us nobody else can object it. So
But
then it happened that ministry took it from their views and then finally everybody accepted it.
But was it a politically motivated decision or not? It was a only engineering oriented sort of decision.
See, at times you have to see practically also. If there are defects in the diaphragm wall, you are investing 60,000 crores in a project, and because of one diaphragm wall of 1,000 crores, the entire project is in jeopardy. What will you do? Yeah, anyhow, for repairing of that, you need to spend 500 crores. It's a matter of only remaining 500 crores. What is a wiser decision? Decision is what has been taken is absolutely correct. But in the Indian system, who will bail the cat? That is the question. COPPA will not say, CWC chairman or member data will not say. Got it? तो ये decision तो लेना है, सही है, ठीक है. Let them make a full-fledged delivery. It should be tested 100%. Integrity should be fine and let the dam come. अब वहाँ पर हम क्या करते हैं, अगर हमें डिसीजन नहीं लेना, आप एक कमेटी बना देते हो ना, कमेटी का बना देते हो, कमेटी बताया, कमेटी ने बताया, तो इसमें 4 इंडिपेंडेंट एक्सपर्ट आ गए, 2 यूएस के 2 कनाडा के, उन्होंने कह दिया तो हो गया. और वो फास्ट ट्रैक भी करना था, न्यू गवर्नमेंट को फास्ट ट्रैक भी करना था प्रोजेक्ट को. दिस वाज वेरी हेल्पफुल फॉर देम एंड अकॉर्डिंगली मिनिस्ट्री आल्सो अप्रूव्ड इट. इट हैपेंड 24 में हुआ, 24
सर डिसीजन पहले ले लिया गया था, उनको कम्युनिकेट बाद बीओए के पास किया है कम्युनिकेट.
बताइए और 1:15 होने जा रहा है. और कुछ क्वेश्चंस?
One question regarding penstock buckling. What was the exactly reason behind the buckling? In case of pressure shaft, hardly come across the buckling issues.
buckling के बहुत केसेस हुए. इसमें या तो वेल्डिंग वाज नॉट प्रॉपर.
Back filling का issue.
हाँ, see, welding would have been the
खाली जब होता है.
This is what I am talking of is नाम लिखा था, I don't know, कड़कपारे प्रोजेक्ट की बात कर रहे हैं. कड़कपारे प्रोजेक्ट में buckling diameter was 1.6 or something, 1.4. उसमें जब आया था हमारे पास तो हम जो है उसको हम बेल्ट को हमने टेस्ट नहीं किया, जैसे हमने श्रीशैलम वाले में किया उसमें हमने रिसर्च में नहीं गए. हमने what we did is we asked them to remove back all those things and then again welding. वो जो thickness is all as per design was satisfied. उसके drawing भी CWC ने दिए हैं. So it's only one part where it's which buckled means उसमें उसके पीछे का जो है ना क्या कहते हैं वो concreting was not proper. The pressure was buckling is because of external pressure. So उससे वो concreting ठीक नहीं हुआ होगा. Pressure आया उस पे वो buckle कर गया.
जो कोई subsidence वगैरह तो नहीं था.
नहीं था वो. और उससे क्या हो वो फट गया प्लेट. तो पानी उस कंक्रीट से निकल के बाहर चला गया, वो जाके उसको एडिट से निकल रहा है. तो बेसिकली वो वेल्डिंग और पुअर कंक्रीटिंग का रीजन. तो इसको करने के बाद इसका fine. I think with this I conclude. Thank you very much.
Thank you.
It was nice interacting with all of you.